Okay, here we go. Try number 2 on this. So apparently I don't know what I'm doing, so did not turn the sound on for my other one. So section 1.4 limits. I'm going to do this again, so it should all be fresh in my head. So let's revisit what a limit is. Okay, so we do the notation, the limit as x approaches a of f of x exists and equals L. So what is that limit? That limit is the height you approach, the height the graph approaches as x approaches a from both sides. So let's just look at a quick visual of this. So if here is point A and here is the height that it approaches as x approaches a from the right, which let me see, right for red. It's actually giving me colors this time, so this is going to end up being a better video for you anyway. So as x approaches a from the right, I'm actually approaching the height of L from the left. Remember, we don't care if we actually touch L or not. And then, oh, I was using blue from the left, but I'm going to have to use a different color because blue is kind of my main. So if I approach A from the left, my graph approaches that height of L as well from below. So remember, we don't really care what happens at A. We're not letting X touch A. So whether you're defined there or not doesn't really matter. But that's really what the limit of a function is. So let's look at a specific example. So let's see, I gotta clear this off and start over. Okay, so let's look at an example, and we're gonna let f of x equal 2x plus 3. So we've got a line here, pretty simple deal. The line looks like this. It crosses the y-intercept at 3, and let's let a equal 1. So we've got 1 here. So remember, a is your x value. So we've got a equals 1 here. So that's a. What height are we actually going to approach? Well, it's pretty simple. If you plug in f of x, f of 1, we're going to get a height of 5. So we actually do touch the height here. But that's also the height we're going to approach as we approach from the right and from the left to x equals 1. Okay, so we're gonna approach that height. So from below, like I'm approaching from the left, I'm approaching that height, and from above, we're approaching that height. So we can say then that the limit as x approaches 1, of f of x, which in this case is 2x plus 3, exists and equals 5. So it's, once again, 5 is the height I approach as x approaches 1 from both sides. Let's go ahead and look at an XY chart or f of x chart, and I'm gonna approach both from the right and from the left. So I should probably let's go from the left first. Okay, so I could let x equal 0.9 if I plug that in here. 2 times 0.9 is 1.8 plus 3 is 4.8. But if I want to get closer and closer from the left, so if I plug in 0.99, that gets a little bit closer to 1. From the left side, double that is 1.98, so that'd be 4.98. If I plug in 0.999 and double that, that might not be easy to do since I don't have a calculator. So I want all but 1/1000th. If I double 1/1000th, it's 2/1000ths. Less than a double, so it'd be 1.998 plus 3 is 4.998. Well, what do we notice? We notice that this is approaching 1 from the left or from below. So, whoa, what's going on here? I don't know why that, anyway, tried to do that to me. But anyway, changing my screen on me. So we just put a little minus sign in the, stop it. Anyway, and why is it trying to move that? I do not want that. Okay, and then this is, I gotta go back to my writing again, I guess. This is approaching a height of 5, once again from underneath. So I'm approaching 5 from the bottom side here. So anyway, we can put a little minus sign in the exponent there as well. So we'll see that more in section 1.6. All right, so let's approach from the right. So what's to the right of 1? Well, 1.1, if I double that, 2.2 plus 3 is 5.2. If I double 1.01, get a little closer, it's 2.02. This is 5.02. If I plug in 1.001, double that, 2.002 plus 3 is 5.002. As we can see, this is pretty obvious. This approaches 1 from the right side, and then my height approaches 5 from the top side. So as I approach 1 from the right, I approach 5 from the top, and basically both of these approach a height of 5. So what I can say then is the limit as x approaches 1 from both sides of 2x plus 3 exists and equals 5. Okay, now we do not want to sit here and plot a whole bunch of points, because we may think this is close, but we could get a lot closer than that, and maybe the behavior of the graph could change. In this case, it's not. This is a simple version of a line, right? Which, is pretty evident that the limit is going to exist. So we're going to end up proving that the limit as x approaches 1 of 2x plus 3 exists and equals 5 as well. So we're going to prove this today also. So we kind of want to get away from this deal. It's good to see what's going on if we're not sure, but ultimately we don't want to be sitting here plotting a bunch of points. Okay, so if I can remember what I did next, let's go here and let's draw this and kind of look in general what I got going on here. So once again, if I've got A and I've got L, so in this case L is my limit. I don't really care if I touch it or not. Okay, but really what I want to do here, and of course I'm going to use specifically A is 1 and L is 5. Okay, for this function f of x equals 2x plus 3. Okay, so basically what I want to do is I want to let epsilon be greater than 0. So epsilon is some tiny number, okay, that we're gonna have a vertical epsilon window around 5. Okay, so then the top side of this window, so right here is my vertical epsilon window. So that would be 5 plus epsilon on the top and 5 minus epsilon on the bottom. Okay, and then just try to use different colors here. If I reverse map this back, basically I want to find a delta window around A. So this would be 1 plus delta to the right of 1 here, and 1 minus delta. And what I want here is I want any x value. So if this is x sub 0, if any particular x, I want it to map, if it's in the delta window here, I want it to map inside the epsilon window. And if I can do that for any given epsilon, then what's going to happen is then we need to find a delta greater than 0, so that what happens? So that 0 is less than the absolute value of x minus a is less than delta would imply or guarantee. So basically I'm looking at specific x's in here, so they just use any x instead of x sub 0, implies the absolute value of f of x. So when I map that height minus the L is going to be, so the difference between the output and L there is going to be less than that epsilon. So for this particular case, I'm going to try and use my eraser function if I can. So instead of A, what did we have? We had 1, right? And instead of f of x and L, we had specific values here. So I'm gonna plug those in. So absolute value of x minus 1 is less than delta would imply the absolute value of 2x plus 3 minus L is 5 is going to be less than epsilon. And then now what I'm going to do is I'm going to use a particular epsilon. So I'm going to go back and do some more erasing. I'm going to let epsilon equal 0.1. So anyway, if I do that, just kind of erase this. So I'm going to let epsilon equal 0.1. I got to get back. And if I do that over here, so I had 5 in the middle, but my epsilon window on the top side is 5.1, on the bottom side is 4.9. This is my epsilon window. Remember, epsilon is a height, or it's a vertical window. It's a height window. Okay, and of course I've got my L right in between of 5 there. But anyway, so I'm going basically for the given epsilon, I'm going 1/10 above, 1/10 below. And of course, for my A here, I need to find a delta. So this is going to be 1 plus delta. This is going to be 1 minus delta. So once again, I need to find that delta so that any x value in here, once again, see if I can use a different color. So if I got any x value, x sub 0 or x sub 1 or just x, any x value in that delta window, I need it to map inside of that epsilon window. So once again, down here, this is a delta window around x equals A. Delta window around A. Okay. This is an epsilon window around L. This is a delta window around A. So, okay. Anyway, so I need to find that. So the question, oh, and then I did not erase here either. So instead of epsilon, I already know what epsilon is. It is 0.1, right? So what I'm going to do is I'm going to work with the last part of this to try and find the delta. Okay, so I'm going to show you that. So I think I can, whoops, I think I can start over and hopefully remember since I went through this already anyway. So let me go back. So we're trying to, once again, epsilon equals 0.1, and so we're going to let epsilon equal that, and we're trying to find the delta. Okay, so that, find the delta greater than 0, so that what? Whoops, so that 0 is less than the absolute value of x minus 1 is less than delta, implies, which I'm going to use an arrow now, implies or guarantees the absolute value of f of x, which was 2x plus 3. Man, why? I don't understand why that does that to me. Okay. Go back. Let me write. Okay. 2x plus 3 minus 5 is less than 0.1. So what we're going to do is I'm going to work with the finish line here. I'm going to work with the right side. And I'm going to go ahead and combine like terms here. And this implies that we've got 2x, absolute value of 2x minus 2, because plus 3 minus 5 is minus 2, is less than 0.1. And then what I can do is I can factor. So that's the absolute value of 2 times quantity x minus 1 is less than 0.1, right? And then if you have the absolute value of a times b, that's the absolute value of a times the absolute value of b. So I'm going to make that evident that that's a 1 inside the absolute value, less than 0.1. Of course, we all know that the absolute value of 2 is 2, so I'm just going to erase that here. So I will let you just skip to that point. And then, of course, what could I do now? I could then cancel this, or divide both sides by 2. And if I divide both sides by 2, my inequality doesn't change, because the only way an inequality changes is if you multiply or divide by a negative number, which we're not doing. And of course, this actually equals 0.05, right? So 0.05 is what this is. But notice I have absolute value of x minus 1, I need to be less than delta. And on the left here, what do I got? I've got the absolute value of x minus 1 is less than 0.05. So that's what I get over here on the right side. So what do you think I want to let delta equal? I want to let delta, so set delta equal to 0.05 or 0.05. So that's what I want to do. And then I'm going to show, basically we can work back up the steps to show that this is the case. So let me do that then and show you how that works. So basically this is leading toward a proof, but this is just for one particular epsilon, not any epsilon. Okay, so we're going to say let epsilon equals 0.1, and now we're doing a let set. So we're doing a let set. Whoops, let set. And of course, set, I started drawing a delta because we're going to set delta equal to 0.05 now. So we're going to let epsilon be greater than, or epsilon equals 0.1, set delta equal to 0.05, and then we need to show that 0 is less than the absolute value of x minus a, which is 1 here, is less than delta, which is 0.05, implies or guarantees that the absolute value of f of x, which is 2x plus 3 minus 5, is less than epsilon, which is 0.1. So what I'm going to do here is I'm going to continue working with the right side of this part, and then show it and basically use those steps in reverse order that I had before to end up over here. So basically the page before this, if I work back up the ladder, then I can see that, hey, this implies, so if I have this side, then that implies the right part of this inequality is absolute value of x minus 1 is less than 0.05, which implies what? That the absolute value of x minus 1 is less than 0.10 or 0.1 divided by 2, which implies I can take that 2 up, right, over here. So that implies that 2 times the absolute value of x minus 1 is less than 0.1, which implies that the absolute value of 2x minus 2 is less than 0.1, which implies, and then once again what I have up here, the absolute value of 2x plus 3 minus 5 is less than 0.1, which is really what I wanted. That was the finish line that I was trying to get to here, right here. So I did show that. So when delta equals 0.1, then I could have delta equals 0.1, then, or not delta, epsilon equals 0.1, then delta equals 0.05 will guarantee that any x's within this delta window are going to map within the epsilon window. So once again, I'm gonna show that. I have no idea how this changes to that. So anyway, trying to figure it out here. Maybe fit screen. There we go. So once again, drawing this out a little bit bigger here. But anyway, there's my f of x. Don't really care what happens at a because I don't touch a. But anyway, this was 1. This was 5. L equals 5, right? My window here around a was 0.05. So that window is actually 1.05 on the right side, and it's 0.95 on the left. And then up top, my epsilon window up top, my vertical epsilon window was 0.1. So once again, that was, I had this written out. My epsilon window was from 4.9 to 5.1. My delta window that I found was 0.05 away from 1. So 0.95 to 1.05. And if you take any number in here in this delta window, then it will map into that epsilon window. So if I take any x sub 1 or x sub 2, anything in there. So for example, if I have x equals 0.99, well, what does that map into? That's in the window, right? Well, we already figured that one out. I think it was 4.98 for f of x. Well, that's in between 4.9 and 5.1, right? We also looked at 1.01. That's in between 0.95 and 1.05. And if we map that up, I believe that mapped to 5.02. So that's also within the window. And no matter what x you have, it's going to map to an f of x, which is in the epsilon window. Epsilon window. So any x's in the delta window are going to map within the epsilon window around L. Okay, so hopefully that makes sense to you. And now we're going to do it in general as well. So get the lights back on in here since no one's around. Anyway, a good day to study. It's raining. Don't have other classes getting in the way of calculus. So anyway, so now, so we found it for a specific epsilon that ought to help you do number 6 in section 1.4. So let's do it now for any epsilon. So now we just want to say, hey, let epsilon be greater than 0. And now we need to find a delta greater than 0 so that those things happen. And once again, I'm going to write this out. 0 is less than the absolute value of x minus a, but I know a for this one is 1 is less than delta, would imply or guarantee that the absolute value of f of x, which in our case here is 2x plus 3, minus L, which in our case is 5, is going to be less than that epsilon. So we need to find the delta. That's what we're trying to do. We're trying to find the delta, right? So if I'm trying to find the delta, what I'm going to do is I'm going to start with the right side, figure out my steps, and then work backwards for the proof. So on the right side, if I know that the absolute value of 2x plus 3 minus 5 has to be less than epsilon, this is for any epsilon, no matter how tiny. So it could be 1/10, 1/100th, 1/1,000,000th, etc. Well, once again, if I go ahead and do what we did before, the only difference is there's an epsilon on the right, not a particular number. So it's 2 times quantity x minus 1. Absolute value is less than epsilon. So this implies that we've got 2 times the absolute value of x minus 1 is less than epsilon. Notice I put little leg and stuff on my 1 when I have absolute value signs by it, symbols by it. Anyway, divide both sides by 2. And so I get x minus 1 is less than epsilon over 2. So this is what I have here. So guess what? I want to set delta equal to epsilon over 2. So that's what I want to do. So set delta equal to epsilon over 2. So for any epsilon, delta to the delta window that I want, and this is going to be the biggest such delta window actually, but anyway, I could set that equal to epsilon over 2. Notice when epsilon was 0.1 that we had earlier, we divide that by 2 and we get 0.05. So if epsilon happened to be 1 over pi, then delta would be 1 over 2 pi. You just divide it by 2. If epsilon was 1/100th, we would take half of that and have delta equals 0.005. So now we have it in general, and we can go there. So set delta equal to epsilon over 2, and so I'm just going to plug that in there. So maybe I just want to do it with the eraser now. I can work backwards if I can get to my eraser. So now I'm going to do, well, I'm just going to clear the whole thing. That might be easier. Okay, so now here we go. All right, so we're trying to prove that the limit as x approaches 1 of 2x plus 3 exists and equals 5. Okay, first of all, for the proof, we'll get into this a little bit more in section 1.5. This has to be defined everywhere on some open interval containing x equals a. Well, the domain of f is all real numbers, so it's actually defined everywhere. So we're fine in this case. But anyway, we're going to let epsilon be greater than 0, and here we do the let set. So now I want to set, what did we say delta was? Set delta equal to epsilon over 2. Then, what do we have? 0 is less than the absolute value of x minus 1 is less than delta. Implies what? Well, what was delta? We're just going to work with the right half of this. This was equal to epsilon over 2, right? Because we set delta equal to epsilon over 2. So this implies the absolute value of x minus 1 is less than epsilon over 2. And then I'm going to work backwards here on my steps. So then I'm going to multiply both sides by 2, and I get 2 times the absolute value of x minus 1 is less than epsilon, and keep going backwards up the list of what we had on the page before in the orange there. So anyway, this says that the absolute value of 2x minus 2 is less than epsilon, which implies that now we can write it as 2x plus 3. So I'm just taking all the steps that I did to find delta on the previous page and undoing them in reverse order. So that implies absolute value of 2x plus 3 minus 5 is less than epsilon. And of course, this is f of x, this is L, this is epsilon. So the absolute value of f of x minus L is less than epsilon. So we are done. Okay, so that basically gives us the proof in general for this particular x, or this particular a, x equals 1, that was a, right? So for this particular a, we know that the limit is 5. So this proves that. So this could also help you do the first one in section 1.5 as well. So we'll do some other stuff. It's pretty easy when you can just plug in to figure out what the limit is. In this case, if we plugged in 1, we get a height of 5, but that doesn't prove anything. We're going to keep it simple. So I'm gonna want you to be able to do this epsilon delta stuff for lines, and when we get into other things, it becomes a little bit more involved and stuff too. But anyway, so this is limit theory and proof of a limit. Remember what a limit is the height that the graph approaches as x approaches a particular value. Okay, so the height I approach is actually 5. So hopefully that was everything I had in the first video. Hopefully I did a little bit quicker so it doesn't take as much as your time, but reach out if you have questions, and I'll try and do another video on some specific algebra manipulation stuff to come up with proof. So when we're not doing epsilon delta stuff, then we still want to know what the limit or the height is that we approach for functions at particular places. So anyway, have a good day and reach out if you got any questions. Thanks.